11.2, conservation of energy. I mentioned last week that you think of energy as money. Where money, if you have $50 in your wallet, for example, that amount of money is a constant unless somebody takes it out, spends it, steals it. But, if you had that much money in your wallet, you came back later and it wasn't there, you would assume that somebody had taken it. It doesn't disappear. Money doesn't disappear, just like energy doesn't disappear. Energy can change form, but it never, sorry, I just went on mute for a second. You can never destroy energy, you can't create energy, you can only change its form. And that's called the law of energy conservation. So this states that in a closed, isolated system, energy can never be created or destroyed. Now, energy can change form. So you can go from, heat energy to chemical energy to sound energy. So, but you can never destroy the energy or create the energy. Do you remember what a closed system is from last chapter? So closed means it doesn't lose any mass or gain mass. There's no mass change. In an isolated system, there's no net force acting on the system. So you could have balanced forces or no forces, but there's no net force acting on the system. Mechanical energy, we'll just use ME for abbreviation for that. It's energy that's used for movement. And so the equation says this, that you can convert between potential, that's what PE stands for, and kinetic, that's what KE stands for. But the sum of potential and kinetic has to always be constant in a closed, isolated system. Does everybody have those down?
Yes.
Not quite yet. Yeah.
Okay.
So Miss Holly, in an isolated system, there can be forces on the object, but they just have to cancel each other out.
Yeah, exactly. That's a good question. Yes. So you have no net force, but you could have forces on either side acting opposite directions. That's a possibility.
Okay.
Okay, so let's say you have a ball on a cliff. I can draw a ball. And it's not moving yet. So if it's not moving, all the energy is potential, there's no kinetic energy. Kinetic energy is 0 if it's not moving. Potential energy would be related to the mass and the height of the ball. Let's just say, to keep it simple, that it's 10 joules. We'd have to use MGH to find out what that is, but let's just say it's 10 joules at this point. If the ball starts to move, at this point now, it's falling down, and it's halfway through, at halfway through, 5 joules of energy has been converted from potential to kinetic, and 5 joules remain as potential energy. And at the very bottom, right before it hits the ground, there's no height. So at height 0, there's no potential energy remaining in the system. So potential energy is 0. Kinetic energy would be at its maximum, which would be 10 joules in this case. So the ball started with 10 joules of potential energy. As it falls down, it gains speed, but it loses height. So as it gains speed, it gains kinetic energy, but it loses height, so it loses potential energy as it goes down. At the very bottom, at height 0, it's 0 PE, but all the energy is converted from PE to KE, so it's 10 joules of kinetic energy right when it hits the ground. Now, it will, of course, eventually stop, in which case there's no energy of kinetic or potential at that point, but this is when it hits the ground, the speed it hits the ground with before it stops.
Miss Holly,
Yes.
your your camera is covering what the PE equals at the top right. What is that?
Okay. Does that help at all or not?
No.
Okay. I'll just rewrite at the bottom then.
Well, all it is what the number. I think it's a joule. I think you said 0, but I'm not sure.
Yeah, 0 joules of potential energy and 10 joules kinetic energy.
All right, cool. Thank you.
Okay, does everybody have that down?
Yes.
So we can look at a pendulum, and it's a similar idea to what we saw with the ball falling down. So a pendulum, just a ball on a string. At this point, if it's not moving at all, there's no kinetic energy. And we'll say there's no potential at this point either. Because on its own, this ball isn't going to do anything. Now, if you cut the string, it's going to fall down. But if you don't give it any energy, it's not going to move at all. So we'd say it's 0 potential, 0 kinetic energy if it's just motionless on a string. But what you can do is you can lift it up and give it energy. So if you were to bring the ball upward over here, you've now added some height to it. So by bringing it upward and you've given it some height, you've given it stored energy. So let's just say that's 5 joules of energy that you've given the ball. Now, if it's not moving, which we'll say it's not, there's no kinetic energy at that point. It's all potential, but you can release it, it will go down. So let's say you do that, you release the ball, it moves back down. So now it has motion. And kinetic energy would be, in this case, 5 joules. It's at its maximum speed at this point. We'd say that there's 0 height when it is at this point. So h would be 0, which means PE would be 0. It has motion though. Kinetic energy has been converted from potential to kinetic. The ball will move upward to the same height you released it at. And so up here at this point, it stops moving for a moment. So it's 0 joules of kinetic energy. Potential would be 5 joules again. So energy can convert between kinetic and potential throughout here. The total amount stays constant, in this case 5 joules. Does everybody have that down?
Yes.
A spring is a similar idea to the pendulum. So let's say the way in a spring is at rest right here. So if it's at rest, it's not moving. Kinetic energy is 0. And if it's not moving and you haven't given it any amount of energy, there's 0 too. So this would be the rest point of the spring. Now, if you pull the spring below equilibrium, right here, giving it energy. So equilibrium would be the point where it's at rest, but you pull it beyond equilibrium, now you're giving it some energy in the form of potential energy. So let's say it's 10 joules. It's not moving at this point, so it's all potential energy. But then you can release the spring, it will move back upward at that point. And it will go beyond equilibrium. It eventually will stop. So up here when it stops, it's 0 joules of kinetic energy. Potential energy would be equal to what you gave it. So if we gave it 10 joules down here, it will have 10 joules up here as well. Now the spring will come back down though. And so as it moves back down, its maximum speed will be at its equilibrium point. So when it passes through where it's usually at rest at this point, it will be the maximum kinetic energy, the fastest speed. So kinetic energy at that point would be, in this case, 10 joules. That's what you gave it to begin with. We just applied the same idea to a spring as we did to a pendulum and to a ball falling. In all cases, energy is being transferred between two forms. Now, because it's not a closed, isolated system, energy doesn't stay. It's transferred out of the system. It's lost the surroundings. So it's lost to the surroundings in the form of sound, heat, friction. If you clap your hands, for example, by clapping your hands, you give energy to the surroundings in the form of sound. You make a sound. So some energy is released that way. Your hands will warm up as you clap your hands. So you also would have energy that's transferred in the form of heat that way. The same thing's true for anything, whether it's a pendulum, a ball, and a string. Some energy is lost in the form of sound, friction, and heat.
Quick question: did anybody else clap their hands, or was that just me?
Would.
I don't know. After you said that, I clapped my hands just because.
But it's, maybe you noticed that, we clap your hands for a while and they turn red and they start to heat up. Anytime you transfer energy, you're going to have some heat. If you bounce a basketball on the ground, the basketball will heat up, both itself and the ground as you bounce the basketball.
I have a quick question. Is friction an energy type, or does friction produce heat and sound?
Friction removes energy. Friction is a force, and it's a force that removes energy from the system. Usually it's a form of heat. Friction itself doesn't, well, it can produce sound, but friction removes energy from the surroundings. So if you clap your hands, you hear the sound of hands clapping. That is due to friction between your hands that create that. Okay, let's look on page 296 and go through the example problem number 2 on 296. So it says during a hurricane, a large tree limb with a mass of 22 kilograms and a height of 13.3 meters above the ground falls on a roof that is 6 meters above the ground. Question A, ignoring air resistance, find the kinetic energy of the limb when it reaches the roof. So I'll start by, it helps to draw pictures. So I will attempt to draw this. That's supposed to be a house. Still not the best house, but we'll go with it. Okay, so it says that a tree limb falls from a height of 13.3 meters above the ground. So it's always relative to the ground. So we know it's 13.3 meters off the ground. And it says that it falls on a roof that is 6 meters above the ground. So it goes from this height to the house. We'll say it's right there. And that height is 6 meters above the ground. So the tree branch falls from here to here. So we went to the energy change. Potential energy is going to get smaller as it goes from this height to this height. We want to know the difference between those two. So what we can do is find the energy it has to begin with at the very top. So MGH would be the equation to use for that. So at the very beginning, it's not moving. The tree branch is just staying still. So there's no kinetic energy, it's all potential energy. So the energy of the system would be equal to potential energy, MGH. We're looking at the mass of the tree branch. That's 22.0 kilograms. And its height is 13.3 meters off the ground. So let's go ahead and find that out. So we're going to do 22.0 kilograms times 9.8 times the height, and it's 13.3 meters. Let's multiply it out. So that should give you 2,800 joules. Actually 2,860, which we have, in this case, I have 2 sig figs. Let's go and just make it 3, just make it easier that way. So 2,860 joules of energy is what it has to begin with. It falls down to the house right here. And so at this point now, it's a height of 6 meters off the ground. So let's find energy that it has at this point using the same equation. Can you all read these? Are they too far to the side?
Yes, I can read them.
So again, we're going to multiply this out, 22 times 9.8 times 6.0. And that gives us 1,290 joules. So the tree branch went from having 2,860 joules of energy to 1,290 joules of energy. So if we take the difference between the two, 2,860 joules minus 1,290 joules, that gives us 1,570 joules. So that energy was lost, and it went from potential to kinetic energy. So as the tree branch fell, it was converting energy from potential to kinetic. And so if it lost 1,570 joules of potential energy, that went from potential to kinetic. And so we would say if it lost that much potential, it gained that much kinetic. And so we would know that the tree branch must have had 1,570 joules of kinetic energy when it hit the house right here. Are you with me so far in this?
Yes.
So the question is asking, find the kinetic energy of the tree limb when it hits the roof. Well, that's 1,570. So we found out how much potential energy it lost as it went down. That would equal the kinetic energy that it gained as it fell down.
Miss Holly,
Yes.
so however much potential energy you lose, that's always equal to the amount of kinetic energy?
Exactly, yes.
Okay.
So that's question A. For question B, it's asking what is the speed of the limb when it hits the roof? So we know kinetic energy equals 1/2 mv squared. We know it's 1570 for kinetic energy, so we'll put that into the equation. The mass of the tree limb, 22 kilograms. We just need to solve for V. So let's go ahead and multiply 1/2 by 22. We get 11 for that. So now we get 1570 joules equals 11.0 kilograms times V squared. Divide both sides by 11. So 1570 divided by 11 equals 142.8. Now we have 3 sig figs for both of these, so it should really be 143. So now we have 143 equals V squared. So we'll square root both sides. And we should get, when we round it, 12 meters per second for the answer. Actually, I'm sorry, we need 3 sig figs for this one. So it should be 12.0. Any questions about that before we go on?
No.
So for today, I want you to work on page 297. Just do 15 and 17 on 297 for today. And we're going to have, just to give you a heads up about this week, I'm going to give you a quiz on a Wednesday. The quiz will be very similar to homework questions that you've done this week. It'll be different numbers, but very similar questions to what you did on homework. So that'll be on Wednesday. And we are going to have, I think I already told you this, but just to make sure, we will have a test next week. It'll be on Wednesday next week. We'll review for 4 days, Thursday, Friday, Monday, and Tuesday. We have the test on Wednesday next week. We'll have a quiz this week on Wednesday, test next week on Wednesday.
How is the test going to work? Like, how are you going to distribute it?
I haven't made it up yet, so I'm not exactly sure, but it'll be a similar format to what you've done, but it'll be multiple choice questions, matching, maybe some working out questions. I don't know yet exactly. When I know for sure, I'll let you know, but it will be a similar test to what you've had for other chapter tests, probably through Google Docs or Google Classroom or something like that, but I'm not quite sure how that will work.
Okay, so similar thing for the quiz. Like, you'll just email something to us on Wednesday that we'll take.
Yes.
Okay.
Oh, and the quiz will not be open book or open notes, just to let you know. It's going to be closed book, closed notes.
So it shows 15 and 17?
Yeah, just 15 and 17, yes.
Wait, so is the quiz like at a specific time we have to do it, or like
No,
the whole like Wednesday?
Anytime on Wednesday is fine.
Gotcha.
And we'll still have class on Wednesday too. I'll go over a few homework questions on Wednesday. So we still have a class, but I won't give you the quiz during class on Wednesday. It'll be anytime you want to take it on Wednesday.
And it's just over everything that you've gone over, right?
Yeah, anything this week. So it'll be
Okay.
any homework questions that we've gone through this week.
Oh, just this week?
Yeah.
Oh, okay. So just today and tomorrow, basically. And Wednesday morning. Okay, gotcha.
Just Monday and Tuesday. Yeah, not even
Oh.
Wednesday, but just Monday and Tuesday.
Okay, perfect.
Miss Holly,
Yes.
do we need to know the skiers' mass in 17?
Let me see. For 17, you actually can cancel it out.
Okay.
Here, I can show you. So what you can assume at the very top of the hill that it's all potential and it's no kinetic energy at all. And at the
Yes.
bottom of the hill, you can assume just the opposite, that it's all kinetic and no potential. And so let's just say that, just make it easy, it's 100 joules. So we'll just say that. So 100 joules of energy is transferred. So down here, it would also be 100 joules of kinetic. In which case, we could say up here, PE would equal kinetic energy down here. So PE would equal KE. And so we could say MGH equals 1/2 mv squared, where the m's would cancel out.
Okay, that makes sense. Thank you.
You're welcome.